Hi, everyone, and welcome to our webinar on Agile engineering and iterative design process in aerospace engineering. My name is Jack Coor, and I'm the research director at Payload. We have a really awesome panel today with representatives from Flow Engineering, Hermeus, ABL, and Planet. We're going to talk a lot about the history of aerospace engineering. We'll talk about kind of more legacy NASA and prime engineering philosophies, and also then move into agile engineering, what it is, and why iterative design going forward. So it's going to be a very open dialogue. We'll have a Q&A box below on the Zoom link. So if you have any questions, please just put them in the Zoom, and we'll try to get to them in real time. So with that, this webinar is sponsored by Flow Engineering. So we're going to go around and introduce everyone. But first, Pari, I want to turn it over to you to introduce yourself and Flow Engineering, and maybe a little bit of your thoughts on iterative design as well.
Awesome. Well, thank you so much, Jack. It's awesome to be here among friends, and it's awesome to be sponsoring this webinar. So very quick background to me and to Flow. I'm Pari. I'm the founder and CEO of Flow Engineering. We are building the world's firstly agile requirements tracking software. We help new space teams design, iterate, verify 2 to 3 times faster than they can do on old school tools like IBM Doors, Jira, or custom built solutions. Our secret sauce, and I think why we are here today, is because we really believe that engineering is going through a once-in-a-generation transition, a transition from the more traditional DoD-based, NASA-based waterfall approaches to engineering to a much more agile and iterative approach. And we think the role of an engineer fundamentally has changed in this, from systems engineering being something who sits in a corner and gets involved every now and then, to really every engineer in an organization needing to be a little bit of a systems engineer. So our secret sauce, what makes us special, is that we help every single engineer, a mechanical, an electrical, an avionics engineer, really own requirements and systems engineering pieces. And that's what helps engineering teams collaborate faster. I'm proud to say that we are working with some of the fastest agile teams in the world, teams including Impulse Space, Stoke, Astranis, but also this wave is so much bigger than just new space. So we're working with some of the foundational fission, fusion, quantum, aerospace companies in the world. And yeah, we're just really, really excited to be here and to be sponsoring some of this discussion happening around this change that's happening in engineering and around what that means for our engineers day to day.
Great, thanks. So that was Flow Engineering. Flow Engineering is sponsoring the webinar today. Now we can go around, and maybe Skyler, we'll start with you. Maybe just quickly introduce yourself and your company.
Yeah, sounds great. So I'm Skyler Shuford, one of the founders of Hermeus, COO, which is kind of a catch-all for what I do now. So a little bit of everything. So really focused internally on our product development, making sure it comes along at the right rate. So merging and organizing engineering, manufacturing, test to make sure that all kind of operates as a single unit. And then making sure that the infrastructure supports all of it in a way that enables the pace that we have to move as a venture-backed startup in this space. So information systems, security, supply chain, facilities, all that kind of good stuff. So making sure that holistic approach is really necessary. And I think that's kind of to Pari's point on, having everyone have that kind of like cross-functional ownership is the way that we are able to kind of do things new, but I think in a lot of ways do things the way they used to be done before. So, in terms of it's really about the industry remembering what it takes to do hard things on very tight timelines. And that's what we spend a lot of time thinking about at Hermeus. Oh, and what Hermeus does, for people not familiar, we're building really fast airplanes. So the big picture, long-term goal is an eventual commercial hypersonic aircraft. The idea there is that the fundamental or like component technologies have existed for decades. So if you set the speed limit of about Mach 5, ramjets have been flying for decades. jet engines for, the takeoff low speed portion are relatively mature. The materials that you need for those speeds are relatively available, off the shelf materials. And so it's more of an engineering problem, not a science problem. On the way, though, obviously, it'd be pretty wild to try to build a commercial passenger aircraft straight out the gates. So for the next, 5 to 10 years or so, really focused on an iterative development process. I assume that'll be a very common theme today for all the folks here, but building aircraft along the way that can do interesting things for customers. So be it in the commercial space, on the flight test as a service side, or in the defense space, that's really our target over the next 5 to 10 years, so that we get the reps under our belt, we can develop rapidly but reliable aircraft, and then fly faster than people have for decades.
Thanks, Ian. Same introductory question.
Yeah, so I'm VP of Engineering at ABL Space Systems. We kind of generally have pretty broad purviews for our VPs of engineering, but I kind of run everything from the avionics vehicle software and GNC to the ground automation control software, ground electronics, and then I actually have the regulatory group as well. So kind of ends up with a broad portfolio. But yeah, I think ABL is focused on bringing a launch vehicle to market and just kind of getting that out there, while also trying to figure out how we use mobile ground systems to enable resiliency and give us flexibility in kind of where we're launching out of. And I think it's always a challenge with launch vehicles, because launch vehicles kind of are a 1 or a 0 thing. Either it works or it doesn't. There's not very many launch vehicles that kind of work and are successful. And so I think that's just kind of one of the challenges with iterating quickly. Means that sometimes you are not successful with your test or with your flight, and you need to learn as much as you can from each of those as you go forward.
Great. Over to you, Quinn.
Yep, my name is Quinn. I'm VP of Engineering at Planet. For those not familiar, Planet designs, builds, operates roughly 200 satellites that focus or photograph the surface of the Earth roughly once every day. And we then we use ground software to build all kinds of data products on top of that data set. And then we've also just launched, we call the Planet Insights platform, which is a software platform to help customers and partners basically shorten the gap between the data and a solution that they're building or insight that they're looking for in the data. I mostly am working on the ground segment stuff, although, like everyone at Planet is concerned with the hardware because that's where our data originates. So working a lot, I'm very interested in kind of the intersection between hardware and software engineering and how you package that together into something that provides value for customers.
Awesome. I'm glad to have the 4 of you guys on today. For the first question, I want to maybe turn it over to you, Ian. And let's just try to contextualize this whole discussion today on iterative approach to engineering and agile engineering by discussing what the legacy philosophies have been, or maybe what are still being used today with perhaps NASA or primes, and how they differ from how the 4 of you look at engineering.
Yeah, I think it's a little hard, I think, for modern or like people who've grown up in the 2000s, basically, to understand kind of the difference in what it took to launch a rocket in the 1960s and 1970s. I think the idea of a hall of draftsmen is just so foreign to all of us. And I've worked at larger primes, and you walk through some of those buildings and it's just these massive office spaces. You're how would you need this much room? And it's because you might have 100 draftsmen, and each of these draftsmen is providing support to multiple engineers and kind of go through this whole process. And I think as we go forward, we realize that we have technology and we have ECAD and electrical computer aided design tools that allow us to basically accelerate that process. And I think that's the biggest change for me, is that you think about the productivity of a single engineer today who is sitting down in NX and is modeling and building a part and then develops that part and outputs a step file. And that could be a week of work, and it's a single person who's doing it. And I think this idea of RE is really enabled by that productivity boost that comes with all of these new modern tools. And I think that needs to change kind of the way we're doing engineering and how much work we can actually accomplish with smaller teams of people.
Right. And can you define RE?
So an RE is really someone who is a responsible engineer, and I think like there's a lot of definitions out there for that, but I think it is really the person who's responsible for making sure that the product like works in context is I think the big thing. I think a lot of times you'll see RE batted around and people think their product works when they think it works, but I think most of the time it needs to work when integrated in the final system and understand its like context within the system and like kind of meet all those requirements across the board, which is a very broad and large task.
Yeah. Yeah. And Pari, you had a LinkedIn post that went pretty viral on this exact topic. I think it was on SpaceX's philosophy on system engineers versus REs. Could you describe what that post was and kind of the key takeaways that you had on SpaceX's philosophy here?
Yeah, absolutely. So I think when people think about what SpaceX does, it's interesting. And then when people get close to it, it scares the crap out of them. Like actually saying these things out loud versus living them day to day as an engineer are very, very different. And I think like if I had to distill down what SpaceX does really, really well, it's they have this core philosophy that at SpaceX, every engineer is a systems engineer. And that sort of comes out this learning that either everyone is responsible for the system or no one is. So if you compare and contrast a Prime or NASA's org chart to SpaceX's org chart, at NASA you have a system integrator and a systems engineer and a sort of overall project engineer, and you've got like 5 or 10 people working on one part. I think what SpaceX does differently is they really instill that the person designing the part needs to be the person that owns the requirements, and they need to be the person that can push back on if those requirements don't make sense. And by having that idea of responsibility, so RE stands for responsible engineer, you're really empowering a design team to make fundamental decisions around what the constraints of those designs should be and how those change over time. The NASA approach is we write down the requirements at the start of the process. We spend 2 years thinking about requirements, then they don't change, and then 10 years later we deliver on those. And I think what we've learned as technology has changed and as we've designed more and more complex system is that the early stage assumptions you're going to have at the start of the project are assumptions. And you're going to be right about half of those, and you're going to be wrong about the other half. And you need to empower engineers to be able to say, hey, I can deliver you this avionics block at 100 kilograms because that's the requirement. Or I could give it to you at 105 kilograms, but I could do it 6 months faster. Do you want to make that trade? And every single engineer in the team needs to be continuously making these trade-offs at the design level rather than some external party coming in and imposing requirements that engineers need to sort of be monkeys delivering to. So yeah, really fundamentally, every engineer in a new team is a systems engineer. Every engineer owns requirements. Every engineer is a core part of pushing back on requirements and delivering that product at the end of the day.
Yeah, I think there's an idea that we spend a lot of time thinking about here at Hermeus is really comes down to like accountability and how to hold accountability for owners. So I think the idea behind RE-ship is similar to like a product manager, could be similar to, I think, if defined properly, a systems engineer. But it really comes down to, it's like, what are you responsible for delivering? What are you actually held to account for to actually deliver? And I think when people do even role definitions incorrectly, it comes down to them, hey, you are this crank turner on this piece of analysis, or you are this, pencil pusher or paper pusher. And so when you aren't responsible and held to account for delivery of something, then there's no motivation for you to improve these things and they start to run away. And so if you're just the shepherd of a process, you're not really delivering anything. And so I think making sure that a team really understands what the outcomes are, and that's the idea behind, I think, being an RE that lends itself to things beyond engineering, but it's like you are ultimately responsible for this outcome, even though your window of responsibility, the actual work that you do, may be not within that, right? So it's like, I don't want an engineer running CFD blindly that is just turning the crank on fluid dynamics. I want someone who's like responsible for making sure the airplane flies, right? And so making sure all of the roles in a company are aligned with those outcomes is something that I think is kind of the critical cultural piece behind, product management as defined as an RE.
There's this really great story I heard a couple of years ago. I'm going to get the specifics wrong, but it was someone that was touring NASA in the 60s. And they were getting a tour of the base, and they saw a cleaner sort of clean up late at night. And they asked the cleaner, it's like 8 p.m., what are you doing here? And he said, well, I'm putting people on the moon. And like, that's the culture you want, where like every single engineer isn't here to sweep the floor, but understands that sweeping the floor helps the engineers do a better job, which helps the people on the moon. And then that overall goal comes ahead of, did I dot all the I's and cross all the T's on the systems engineering process?
Yeah. So Quinn, to me, it sounds like that philosophy can lead to maybe too many cooks in the kitchen and maybe less domain expertise. I think there's a pretty well-defined hierarchy in leadership that has been around for tens of thousands of years, where you kind of have specialization and it builds up to more centralized leadership that can make and execute decisions theoretically in a more efficient way, rather than having a lot of birds chirping at once. How do you manage that dynamic? I assume that you also implement this type of kind of network of responsibilities as well, but how do you keep everything organized?
I mean, look, there's a number of ways that you go about that, or at least we go about that. I don't think there's one right way to do this. So, I mean, first off, I think we've been circling a number of things here, but one of the key differences that I see in like a more waterfall based approach to an agile based approach is having like a clear, like in a waterfall based approach, you have a clear sense of what you're supposed to do. And in agile, you have to have a clear sense of what impact you're trying to have, so that as you go through a number of iterations on it, you can see like, it's not about, am I doing the thing that the requirements say I'm supposed to do? It's, am I having the impact with those changes that I'm expecting to have? And, shipping and whatever that means for you in shipping frequently enough to know, is that happening and should I be adjusting along the way? So first off, you have to be clear with people about what impact you need them to have. And so rather than a more traditional project management where you're saying like, okay, these are the list of requirements that I need to get done. I need team A to perform X task, and team B to perform Y task. It's like breaking down the impact that you want to have into those groups so that they can have some autonomy in what then going forward. And then within those like autonomous teams that you're building to go after these, it's role definition to make sure that people know, not just the impact that they're trying to have, but the role that they're playing in that impact, right? And like, we would use a more kind of, I guess, perhaps traditional in the software world, but like product manager, engineering manager, technical lead, and building some of these things, but they each have like a fairly clearly defined role. And certainly, there's a pretty standard definition, and then they can further define it amongst themselves. So they know, okay, I'm trying to make this impact as a team, and my role to play in making that impact is, understanding the customer or requirements definition or like technical soundness of the solution, or, organizing the people to get that done. And basically like with those role definitions and with a clear statement of what we're trying to accomplish, you can iterate and measure toward that.
Great.
I think that,
Go ahead.
I was gonna say, I think that's a good point, because I think the as the leaders of that organization, like I think the key is to create like enough of a vision that people actually can self-align. And I think that's actually the big turning point. Is it's like, if you have to tell every individual RE where they're going, like by the time you finish telling the first person or the last person, the first person is going the wrong direction. And I think that's where, like, as you start to like, as you try to build an organization that does this, you need to make sure that there's a clear enough vision of where you want to be and what you're trying to do, either at the company level or at a discipline level. You basically can kind of like build a corporate machine that like self-aligns into the where you're going. Because to your point, if everyone's just kind of like trying to do the best thing that they think without really a clear like high level vision, then you can end up with the company just kind of like spewing off into multiple directions.
But I also think the role of an iteration is so important here. The thing that I've seen the absolute best organizations and the best leaders in the world do is really downscope and go like, hey, we're a group of really smart people. We could do everything that we wanted to do and we could solve all these crazy problems. But what are we trying to do on the next iteration? What are we trying to learn from that? And how do we just continuously downscope and just be able to not necessarily have technical risk, but really reduces schedule risk. So if we're able to continuously iterate and we're able to, if we don't get on this iteration, we'll get on the next iteration. But by continuously downscoping, you sort of clarify what people need to be thinking about, and then what's a future problem that is a real technical problem that we need to go solve, but we might be able to do a little bit later on. Skyler, I know you had a lot of thoughts around the impact of sort of scope creep. What do you think?
Yeah, definitely. So we put it out in a couple of videos that we released, but I'll hit it again for this audience because I think it's relevant. But when you think about timelines for delivery of complex systems that are 5 years, what ends up happening is there's so many interfaces, so many interactions. You try to define them all at the beginning. You don't know, you hit issues, and then those issues start to cascade. And so the more kind of like parallel lines of effort that you have, that you are net new parallel lines of effort, those issues that come up then cascade, and you get exponential runaways on the order of something like 2x, 3x, 4x on these 5-year timelines, and then you have things just completely run away. But the idea is if you use as a requirement time, rather than it as a resource, you set the requirement on time and then you force as much scope into that time, then yeah, you still may have net new learnings that drive some slippages, but those slippages are less runaway. They are more contained to what you need. So the idea here is that if you have tighter timelines for cycle time, for us it's like a new airplane a year designed, built, and tested from scratch, which is pretty unheard of, but it also forces you to think differently about the scope that you put into those systems and how you think about organizing your teams. And then you're having, maybe at most, 10 or 20% runaways. When you stack those, the amount of learning that you have per cycle for the entire team, not just, the design team, not just the manufacturing team, but also the test team. Now everyone is kind of working together towards your problems. And then you are being able to realize those, every single year, those learnings into your development approach. So you can compound those over time, and rather than having, a 3x, 4x, 5x runaway that because everything kept slipping and slipping and slipping in a cascading way, you're able to just stack a few of those and then end up where you wanted to be at the beginning, but in a much faster way that is much more predictable on the end timeline, less predictable on the intermediate timelines.
So you're saying that it's less costly or cheaper to build something and fail quick and learn from those mistakes and move on to the next iteration than it is to use time and suck through time.
I think sort of. Yeah, sort of. So I think there's an anecdote or like a phrase that I heard is from the like amateur telescope world, which is like it's easier or it's like faster to build a 3-inch telescope followed by a 6-inch telescope than a 6-inch telescope straight out the gates. And I think the same can be true for hardware development of complex systems. So for us, like the first thing that we went and built beside our engine demonstrator that we had was basically a jet powered go-kart, because we had to get reps with the team of a full life cycle. So if we were to wait until, if we were going to let's go build a Mach 5 vehicle straight out the gates, then, 4 years into that 5-year timeline, assuming we stayed on timeline, is the first time that the test team would even get a shot to start working, right? And so and that's not to say that things don't also just run away. So it's like you're getting more reps with the team and getting those feedback loops of like being able to compress. And then I think the other piece here is like for new development, a good chunk of the costs are just driven by time. And so it's like, it's the old story that like your work fills the volume that you give it. So creating that constraint can drive simpler solutions, which end up being cheaper. You deliver on faster timelines, so your labor hours are a lot less. So I think the net outcome of that is that, the systems end up being a lot cheaper in a kind of compounding way.
Yeah, I think the thing that I've been thinking about when we're doing the more like agile / like tactical planning, a lot of times the question isn't really necessarily like what are you going to do, it's what are you not going to do. right? It's like you have to actually like, and that's partially what I've tried to use it to do with my teams, is to empower the engineers to, like, when they do their planning cycle, say like, okay, what are the things that we can accomplish in this 2 week period? How do we accomplish that? And then, like, what are we not going to do? Because I think it's really easy to just get overwhelmed. Like, I have 10 million things that I need to do to get to this macro goal. And then you just kind of end up you get all of them 10% done. And then you end up discovering everything at the very end when everything gets 90% in the same week. And then you're, to Skyler's point, completely blown out of the water on schedule because you have late breaking integration problems, or systems don't work, or someone switched like the position of something. And I think that's really the key, is like focus on getting tasks completely done as quickly as possible to like unlock the discoveries. Because I think that's like where I've seen the cardinal sin of like a full Gantt for like a massively complex program, right? A Gantt chart, like a waterfall, like let's make all the relations. It's like, how do you build that schedule? Do you say like, oh, we're going to have like one minor integration miss and then one major system interface miss, and that's going to add like 3.5 weeks to our schedule? And it kind of ends up being this kind of like ridiculous game where all the engineering managers are trying to add some margin so their team doesn't get squished. And I think just focusing on like getting through, finding the unknown unknowns, and then working towards the most aggressive schedule possible is like really kind of what you need to do. And that's not to say you shouldn't have a strategic schedule that says where all the parts are, look for the high nails and shift resources to try to make that accomplishable. But I think that's like this key part of it, is like you need to get through the first couple of tasks to figure out what you really don't know when you started. And if you don't, then you're just going to always be stuck.
The biggest issues that we have as engineers are integration issues, right? It's not typically that my valve didn't work. It's that something affected this, which affected that, which meant my valve didn't quite work in the way I expected it to work. And I think the thing that Agile gets right, and sort of like everyone here is touching it, is you kind of have to start integrated, and then you stay integrated throughout that iteration process. So you look at the MVP and you're like, hey, what's the smallest integrated piece of customer value I can ship as quickly as possible? And then I'm going to rapidly add capabilities to that on a fixed timeline basis, as opposed to the NASA approach isn't bad, right? It's built for a very specific reason, which is NASA need to get it right the first time. NASA have been developing SLS for, I don't know, like almost a decade now, and they've invested $24 billion into it. And if SLS goes up and it's a huge failure on the first iteration, they don't have that much sway on the public, like on public funding. But what we have, and I think is a rare opportunity for us, is we can say, hey, look, I'm going to probably blow up my next 3 iterations. And that's fine, because I'm not optimizing to get it right first time. I am optimizing it to learn. And if that learning piece works, then the next iteration is going to be trivial. But learning is very, very difficult, and being okay with like downscoping to learn is so important.
Yeah. So Quinn, I want to ask a question to you, Quinn. So Pari, you brought up a lot of interesting points there. One was that NASA's beholden to taxpayer dollars, congressional allocations, and they want to get it right in the first time. But all 4 of your companies are also beholden to investors, which it's a different risk appetite. But Quinn, like you Planet has investors, and you have to do right by them. And the idea, how do you marry that with, as Pari said, blow a couple things up first? How do you marry that with also making sure that stakeholders feel comfortable in the risk that they're taking in your product and company?
Yeah, well, so first of all, you don't want to blow things up. And so, like if you can avoid that, great. But I actually think, look, integration issues are certainly like one of the biggest engineering challenges that we might encounter, but there's like a more sinister, I think, challenge that's lurking in there, which is when you're building in a waterfall world, like you don't know, like you have a hypothesis that the thing that you're building is the thing everyone wants, but you could very easily like build it, solve all your integration issues, get there, and realize that in the 10 years it took you to build SLS or whatever it ends up being, that by the time you finished it, like something else is needed. And So like that to me is like a major risk here, and one that like investors are also afraid of. So like investors don't want to give you money and say like, hey, like we'll give you 10 years, like get back to us when it's ready, right? Like they want to see what the incremental progress is and that you're making it and that you can react to the world changing around you. Because things that are a market need today might not be a market need 2 years from now. And you have to be able to adapt to that. And the only way that you can adapt to that is to have a high iteration speed. And so basically being able to learn along the way is critical, and not just learn from your own internal processes about like what's working for us, like what does our test team need, like what does another team need, but also learning from your customers and saying like like are we building the right thing? Is it working for you? For us, like, are the specifications of imagery that we're producing solving the problems that we expect them to be able to solve, or do we need to adjust those somehow? And that's something that you only learn by getting the data out, and or for us, getting the data out, getting the solutions out. But for anyone else, it's like getting your product out and getting some validation on it from folks, so that you then know, like, okay, this is what we need to do in response to that. Like, this is how we need to build differently. So, like, I don't know of the other companies, like, I'm not sure what those parameters that you might be changing could be, but you're always learning, you're always iterating, you're always figuring out, like, what are we testing in the next version of this? And I think the other reason, or the other way that you can be accountable to, in this case, investors, is by being clear about what you expect to learn from each iteration and what the key metrics are for those learnings. So, they might not be like, hey, this is the one that's going to lead us to profitability. It might be like, we're expecting to learn about the interest in a particular feature, or we're expecting to learn how this new system operates in the environment. And like, this is what we expect to see from it, defining success and failure for yourself in that. And then knowing, like, did we succeed or did we fail? And what are we learning from that? I think is how you maintain accountability across that. So it's not just kind of like throwing spaghetti at the wall and seeing what sticks. You have to have a hypothesis at the beginning, and then you test it.
Yeah. Yeah, I think Planet is such a great example because in many ways you pioneered these low cost satellites where you can have high iteration on it, and you know test things out in orbit, and learn from it very quickly. Ian, how does ABL think of that philosophy of quote unquote, as Pari said, potentially blowing something up because ABL's hardware is much more expensive than Planet's hardware. So there's going to be a different risk appetite. But then again, we also see SpaceX doing it where they blow up starships every couple months, and you can see it's really visible and it's pretty impressive because you can see every couple months the progress that's made. But yeah, I just wanted to get your thought on that, Ian.
Yeah, I mean, I think hardware and launch attempts can be incredibly time intensive. I think I wouldn't say necessarily the gross blowing things up, but I think there's a bit of like, when I think about it, it's like internal customers, and it's like, how do you work? Like, we have a lot of groups, and they're all doing slightly different things, and a lot of the times it's like, when I'm thinking more of the quick iterative processes, it's actually like, how do we work with all those different teams across functions to like deliver data quickly and like verify if things work in a way that allows us to get the mission assurance that we want when we launch. And I think that's where we really want to focus, because it is like, to Quinn's point, like, people don't really want to, like, we don't want to lose big pieces of hardware, and we want to be taking intelligent risks, but also not taking too much risk and not stopping forever because you can't recover all. And I think it's just balancing that. But when I think about iterative stuff, it is really on this, like, it's like, how do I work quickly to develop it, to Quinn's point, internal value, and make sure that with the people, when someone from another team asks me for something, then how do I make sure that what I give them is the right thing? Because probably like 50% of the time, even if we spent like 3 weeks trying to figure out exactly what they needed, either it's out of date by the time that you get it to them, or it wasn't the right thing when they started describing it because they don't really like understand the implications to your system. And it's like, you really need to get in there, deliver a thing that meets what was discussed, and then figure out if that's actually what you need to solve the problem.
Yeah, thanks. And Skyler, this one's for you. I'm curious on how this philosophy impacts employees and how it maybe motivates, but also puts potentially more burden on engineers?
Oh, I think it's definitely harder. It's like short-term harder, and I think long-term beneficial. Having a lot of ownership, having a lot of freedom, but being held accountable to that can be stressful. And so I think it's really comes down to making sure that teams are communicating well, that leaders are keeping a pulse on their teams and making sure that people aren't spinning their wheels or getting too stressed. And so it's a constant like focus and kind of like battle to make sure that we're finding the right balance there. But ultimately, I think it's the inertia can pull you so easily into trying to, have automation or have processes that do the work, but ultimately the work can only really be done by people until AI engineers get better than all of us. But at this point, we're not there, and it's really about like having people like spend the cycles like using their brains is really what we want to do. So it's like even for like data processing, it's like what should drive the critical path of the cycle of like data on the system offboarded to an engineer, them thinking, and then make some changes to the system and get it back in the air. That to me, the long pole of that needs to be thinking, not like data in transit, right? And so it's like making sure the right things are actually driving schedule. And so that's just a constant communication. So it's how do we get a few dozen people aligned? Is it constantly evolving thing? How we use tools to communicate cross-functionally. But it can be overwhelming, especially when almost everyone coming out of traditional aerospace have been in environments where it's very much they are told, hey, this is your job, turn this crank, this is what we expect to see, tell us when you're done. And that can be, that's a lot. And so it takes time to get used to that environment. It takes time to really reinforce it. And then it takes time for the benefits to actually be an emergent property. So it's you can create that environment. It actually gets worse before it gets better because now things are less clear. Things are not as obvious. Things are not like, hey, you better go do this or else you're fired, or you deliver on this timeline and you beat that timeline. It's like, well, what should the timeline be? How fast can we do it? It's okay if we slip. We can be less precise, but like we're actually delivering sooner. Like all of these like assumptions that you make every day, really, in most companies on project management, end up being questions that like we call into play. So I think it's something where the work is really never done, and so it really you have to have the physical and emotional stamina to operate in an environment like this. But I think that's where the like really really powerful impacts end up happening.
Yeah, and Skyler, you mentioned tools that can help ease the process. So maybe I can, Pari, you can jump in on this one. I know we have a bunch of questions in the chat, and one of them is how does flow engineering help with this process and help with iterative design, speed, and reliability?
Yeah, awesome. I would love to talk about flow, but I want to finish up on Skyler and sort of Ian's point quickly first. I think there's a false dichotomy in this, that the blowing stuff up method, or like, let's say the iterative learning method, is slower or more inefficient than the more traditional approach. I mean, the obvious numbers here are SLS versus Starship, or like Boeing Starliner versus Dragon. I think there was a great Ars Technica report recently that sort of mapped out the cost and the time difference between these two. And fundamentally, that was driven by this iterative versus the traditional approach. I think where it gets really hard on the engineers is rework, right? Engineers hate rework. Engineers love to be efficient. And the dream for an engineer would be, I do the thing that I need to do. I do it once, I do it perfectly, and I never touch it again. And that is fundamentally at odds with Agile. Agile is actually way harder in the short term and requires you to manually do something, get it wrong a little bit, have a chat with an engineer, do it again 3 or 4 or 5 times to be able to ship something short term. And that's really emotionally difficult for engineers to sort of come on board with. But the impact of that, like unequivocally falls through, right? Like, so where Agile is tougher day to day is that we will realize, hey, we need to go make a change over here, and that means my model's now out of date. I need to go do that again and again and again. But where that stacks up is like 2.4 billion spent on Starship or the public numbers versus like I think in the order of magnitude 20 billion spent on SLS, and unequivocally we've made more progress. And then with that comes iteration speed and the cost of it, right? The cost of a year, as Skyler says, for an engineering organization of 1,000 people versus the cost of 6 months versus the cost of 2 months. Like that's really where you see the impact. So Agile's messy, Agile's inefficient, but Agile helps engineering teams learn far, far faster. And then going on to the tool side. So you never want to automate too early, right? If you build, it's better to do it manually 3 or 4 or 5 times. But if you know you're in the process of communicating information, models being changed, and then you rebuilding this model 3, 4, or 5 times, if you know you're going to fall into that, that's where tools can be really helpful. So I think the best analogy here is the software engineering industry. Now, software isn't hardware, and when software breaks, things don't blow up and people don't die. But I think it's a really good analogy for the transition that happened. And sort of like, Quinn, I know you've seen this up front with CI/CD. Ian, I know you guys use a lot of that at ABL. The core invention that we made in the software engineering world is this idea of CI/CD, which stands for continuous integration and continuous deployment. And it basically says anytime you make a change to your software base, you are going to run a series of automated tests, low-level tests called unit tests and high-level tests called integration tests. And the simple philosophy of continuously and automatically testing your design against your requirements was the core unlocker that helped the software engineering industry move from annual or quarterly releases to now where we'll release software 3, 4, 5 times a day to production and never see any issues come about. So that's certainly what we're building at Flow. We're building sort of this paradigm of continuous integration and continuous verification and doing all the plumbing work so your engineers get the fastest information on what is working and isn't working. But sorry to plug Flow a little bit. I saw an opportunity. Ian, Quinn, I know you guys are huge proponents of CI/CD, especially when it comes to software in systems. I love your guys' approach to this.
I mean, I can start and just say, look, there's in the world of agile engineering, there's Google has done some study and it basically came away with like 4 key metrics of what you should be measuring to see, like, is it working for you? And it's deployment frequency, or like how often you are deploying your changes to production. It's like lead time for changes. So if an engineer makes a change, how long does it take for that change to be reflected in production? How often are your changes causing a failure? So how often does, a change cause a breaking change? And when you do break something, how quickly does it take you to recover? Are basically like the 4 key things. And if you drive those 4 key things down, you can feel a lot of confidence in making changes. And even if they break, like, you recover quickly. And like if you have a change that doesn't break, but you didn't like it, like you can revert it, or you can roll forward, as they say, instead of rolling back, by saying like, okay, instead of rolling back to the last known good state, like I'm going to push forward into the next state that I think is the right one to be in. And so like really focusing on those 4 key things and actually not necessarily worrying about like, am I going to break everything when pushing? And I need to test extensively to verify there will be no breaks, but knowing that like I have the right observability in the systems to catch a failure before it becomes catastrophic. And I think there was some discussion earlier on like, is this fail fast approach a good one, or like, hardware is quite expensive. And I think, like that's all true, but Agile doesn't mean that like you do the whole thing every time, right? Like you can work in a system of systems. And so like failure might not be like we did a launch of 36 super doves and like they all failed catastrophically. It could mean like I blew up a board on the test bench and I'm okay with that. And so I think like thinking about these as like a system of systems, thinking about avoiding catastrophic failures of the whole system and losing everything by having like the right levels of observability and testing and being able to like iterate fast on designs and manufacturing and deployment, like, again, whatever that means in your specific hardware context is important. And I mean, look, like, it's also in a shared hardware software context, because you have software running on the hardware. You might also have software running, at least for us, in a ground segment, and you just have different risk models for each one of those things, and apply them as you iterate quickly.
Yeah, no, I agree with that. I think the system of system things is actually really good. And I think that kind of goes back to my point where it's like you need to like build and deliver value to your internal customers quickly, and that is kind of that system of systems, right? Like whatever you're doing, you need to prove that it works in the micro before you like step all the way up into the macro. But I do think CI/CD is like a really is a huge part of like how you go faster, and I think it's even broader than necessarily sticking like strictly to software. I think there's a lot of opportunities in hardware, and like how do you build like a good tool system that allows you to basically like run some of the hardware aspects in a more automated fashion. And so whether that's like using Python scripting to make sure that your harnessing ICD like matches up with your intended design, or whether that's like making sure that you account for masses like correctly as you pull through the entire model, and like doing that in a deterministic way is actually super valuable. I think one thing that was really kind of an inspiration to me when I read about it is kind of like the Google SRE approach. And it talks a lot about this, like you should 30% of your day should be toil. And I think Skyler made a good point with like you should be working, like you want your engineers working and you want the long pole to be thinking. I think the problem quickly becomes if you don't start thinking about how you could automate it when you start the build process, you actually end up having your engineers just toiling. And so you kind of end up building a machine that actually like uses engineer blood, sweat, and tears to keep running. And you just have some poor like engineer who's like shuffling data back and forth, or like making PowerPoint slides or making a plot. And I think like a lot of those tasks are actually fairly repeatable, and like pushing people to either say like, if you have a software background, think about how you would automate this, think about the hooks that you need to make your job so it's not your job. And then also like, if you can't, write down exactly what you're doing in a way that you can hand to someone who can automate it for you. Say, please help me, because I spent like 20 hours last week making PowerPoint, or making a plot so I could look at the data. And I think that's like a really big part of like how you have a smaller team and get a lot done is like basically like driving like repeatable tasks to be some repeatable tasks that take no thought should be done by machines. And that's not AI. That's just like basic scripting or basic automation or CI/CD, some variant of all those different tools kind of strung together. And that's really how you enable it. And I think at ABL, like we've really focused on like building up like a unified time series database for all of our test data. And I think that's actually been a huge enabler, because now we have a single set of tools that interacts with that and then pulls out like our data and plots and makes it easier to then build these like complicated systems, because a rocket is really complicated to like generate stuff, and in the long term will give us the ability to trend data and understand like how a vehicle performs versus how we intended to perform.
I think that's a great analog to something that also exists in software, which is, like CI/CD is fantastic and should exist and everywhere where it's reasonable to implement it. But there is you can look at it as, and you mentioned Pari, like a testing framework that runs against it to verify that nothing's going to break. The reality is like you can't verify that nothing's going to break. Like you can have some tests in there, but I think that time series database is like a great flag on how important observability is, and understanding like when you make a change, you have to be able to measure what's going to happen as a result of that, and then provide that data back to people. And that's almost, in some cases more important than a testing framework, depending on, like what your tolerance for something failing is.
But then building the culture to know what the question you're answering with the time series data is like the core of it, right?
Exactly. So knowing, like, not just knowing what you're testing, but being able to like measure it and verify, like, is it working? Am I measuring the right things? What am I seeing? Is critical.
Yeah. We have 10 minutes left in our discussion. We had two culture questions that Skyler, I think you answered, but I think would be appropriate to bring up here on how do you change a aerospace culture. So let's say you have a entrenched culture that is more aligned with traditional philosophies. How do you bring that to more of the agile methodology. And Skyler,
Oh, go ahead. Yeah, Skyler can take this one.
Yeah, I can start. So yeah, the question being is like, is does you have to start it from day one? And the answer is no. Like, yeah, the best time to start it, I guess it's like planting trees. It's like the best time to plant a tree was 30 years ago, but the second best time is right now. So I think culture is really the same way. But it's culture is not fixed, and I think when people start to think of it as being fixed or like we have solved culture, then they're inevitably doomed because it's a moving target. And so I put this in the chat, but it's kind of like a squishy ball where you squeeze it and then something kind of pops out and then you push that side in and then something else pops out somewhere else. But everyone needs to kind of constantly be like looking at it, talking about it, figuring out what it needs to be. I think the scale of an organization can change how much time it takes for culture to shift in the direction that you want it to go. And it really needs like enough people working on it, communicating about it, and trying to improve it. So if you're at a very large organization where leadership is not enabling those conversations or not creating the structure for it or not incentivizing it, I think it can be very hard. I think it's probably possible, but it looks something more like an insurgency for good rather than something that's kind of structured. But I think if you're a smaller organization or if you can get the right kind of like layers of empowered authority to be able to help support it, then it can move faster. But it's something that's it's constantly a challenge, even at us when we're about 200 people.
Yeah, I think the insurgency is a good kind of point on like how you could approach how you have to approach it. I think like really like it goes back even to the iterative discussion we've had about demonstrating value. It's like you can't assert that your culture is better if you haven't done something with it, right? Like you actually have to like demonstrate value. And to your point, if it's in a large organization and you're like struggling to get traction, like I think the thing you need to do is say like, I did this thing and here it is, it works, right? And like, here's how I did it. And here's why this was like fast or efficient. I think for me, the framework that I use a lot with engineers that I really like is kind of this like triangle. Can you imagine the top is kind of like the business like sense, and the right is like this like tinkerer like working in your garage and like kind of like always kind of changing things to change things, and in the lower left is your like scientist where it's like absolute and ideal and perfect. And I think the thing kind of with this whole RE concept is that you actually want to be in like the dead center of that triangle, right? Like ultimately all these businesses are here to make money. We need to balance cost, which generally correlates strongly with schedule. Like we can't just keep changing things to change things, and you can't be ideally perfect because you're just going to run out of there's always more room to improve. It just costs like exponentially more time. And I think that's kind of what I see as like a pretty strong culture is like you're going to always end up somewhere in that triangle, right? Whether you're like business focused or whether you're like just changing things to change things, or whether you're like trying to get something too perfect and like letting perfect be the enemy of good. And I think that's really like what I think about when you're trying to build these iterative cultures. You want to try to center that. And if you can do that, you can get a lot of value out of that.
I think there's something quite important. So I run a software company, which is very different to a hardware company. But the analogy I use with my team is the right culture and processes for the SAS, the Special Forces, are very different to the right culture in the Army, And you really have to understand what team do I have today? What culture makes the team that I have today successful? And then how do I move to a culture that works for the things that I'm trying to hit? We've made a very, very explicit decision that we are going to be light on the process and really instill responsibility. But we've been able to do that because we've hired for people that self-select in for that process. I think if you took NASA's culture and you stripped it and you put it into a Hermeus, and you took a Hermeus's culture and you stripped it and you put it into a NASA, I think both these organizations would fail, despite both those organizations succeeding with the culture they have today. So we're speaking a lot about a very specific style of culture, a style of culture that builds accountability and instills responsibility and lets A players get on with the work that they know they have to do. But I think the realistic approach is you have to know where you're starting today with a team that you have today, and you know where you need to go aspirationally, and then you have to realize culture is a moving target, and you can grow culture in one direction or another.
Yeah, like I think that's right. I think you can change culture. I think it's really hard to do it bottoms up. I think oftentimes like it's got to be a tops down push to change culture. And, like you can break things you don't expect to break with the team that you have when you go to implement culture change. It also like change takes effort. So that's effort that you're not spending on anything else you might be doing. So you have to evaluate like, is that the most impactful way to expend effort that you have, right? And I mean, that assumes that you have a good culture in place that just maybe isn't an agile one, right? And you can be a successful organization without being, agile if the circumstances are right around you. Although like I would argue increasingly it's hard to be successful if you're not incorporating, like the world is changing around us very quickly. Like at a faster rate, like all the time, like the rate of innovation is increasing. And so like everything's changing all the time. Like how can you not react to that change? If you don't speed up your iteration cycles and learn every time you're pushing something out, like, you're going to get lapped. Maybe you'll be lucky in that like what you chose to go forward aligns with where the world is going, but like more likely the world will change and, the thing that you thought was going to be true 2 years from now when you finished will cease to be that way.
Guys, we are running out of time. This has been a really awesome discussion. We have a lot of unanswered questions, like maybe a dozen unanswered questions in the chat. Maybe Pari, can you provide your email address or your LinkedIn or any way for people to contact you so you can kind of follow up with these questions?
Yeah. So if you want to connect with me, please just add me on LinkedIn, linkedin.com/Pari Singh, PariSingh. My email is pari@flowengineering.com. If you have questions or comments, I've been having people send me papers they've written to try and convince their teams to operate in a more agile way. If you have any conversation you have at all, please do reach out to me or the people on this panel, and would love to support the community in whatever way we can.
Great. And Ian, Quinn, and Skyler, thank you for joining us as well. Can people find you three on LinkedIn as well?
LinkedIn works.
LinkedIn. Okay. Well, this has been awesome. Appreciate everyone who tuned in. Really, really interesting discussion, and want to thank you for joining the panel today.
Thank you so much. Super interesting conversation.
Yeah, it really was. Thanks a lot.
Thanks, y'all.